This is going to be the lecture over section 6.2. In section 6.1, we dealt with an uncharged particle or a wave packet, depending on how you want to look at it, a photon, and how it interacts with matter. Now we're going to be looking at the interaction of charged particles with matter. How does that change things? As we've seen, the neutral particles set charged particles in motion as they interact with matter. And it is these secondary charged particles that deposit energy in the material. That's only half of it. Charged particles themselves can sometimes be the primary radiation. Electrons with energies ranging from 5 to 20 MeV are commonly used in radiation therapy, and no doubt you've probably encountered that up to this point. Protons and heavier ions are also sometimes used for therapeutic purposes. The charged particle interactions will be considered here, and they're primarily Coulomb interactions with either atomic electrons or the nucleus. So, this is going to be different from the interaction of neutral particles, like in 6.1. The photons are going to undergo a small number of interactions before they either exit the material or they're absorbed, and that, if you remember, they are exponentially attenuated. That was a lot of the problems that we had worked in previous chapters. However, charged particles undergo a very large number of interactions before they exit the material or losing all of their energy, and this diagram up here is an example of a path followed by an electron as it loses its energy in the matter. And a 1 MeV electron may undergo 10 to the 5th interactions before it loses all of its energy. That's quite a few. They do have a definite range. We'll get to that a little bit later. And beyond this range, no particles are to be found. Charged particles form trails or tracks of ionization in the matter that they traverse. So we've got two types of charged particles from the point of view of interactions. We've got light charged particles and heavy charged particles. The light particles are electrons or positrons, basically the smallest particle of matter that we know that we can manipulate. The heavy charged particles are everything else: protons, alpha particles, pions, heavy ions, so on and so forth. And there are going to be differences between the two because of the large mass difference. Remember that a proton is going to be about 2,000 times the mass of an electron. Heavy charged particles follow relatively straight paths through matter, and it's because they're heavy. You can't easily deflect them except if they encounter a nucleus, and they're not really bothered by electrons. So if you recall the discussion of the Rutherford scattering, in which the vast majority of alpha particles are only scattered through small angles in traversing the gold foil, in contrast, electrons are easily scattered because they're a smaller mass. Electrons are easily scattered by high Z nuclei because of their relatively low mass, and the fact that you have a high Z material means you got a high number of protons that it would be attracted to. And that's the reason that electron backscattering is going to be important when high Z materials are used to block electrons. But we'll get to that. All right, if we're looking at electron interactions with matter, electrons incident upon matter will interact either with atomic electrons or with a positively charged atomic nucleus. As the electrons go through matter, you can interact over a long range with atomic electrons in the medium. These electrons in these atoms are promoted to excited energy states. A small amount of energy is transferred from the electron that's going through to the electrons that are already in the material. And these are referred to as soft collisions because the electron really doesn't get that close to it and imparts a very small amount of energy. But the Coulomb force ranges over a large distance, so there's a lot of these that can occur that may not be very close, but since the Coulomb force is something that can be felt for quite a distance, it doesn't take all that much for you to have a large number of interactions. If it passes really close to an individual atomic electron, it will interact primarily with that electron, and that will get most of the energy. That is considered to be a hard or knock-on collision. The electron is then ejected from the atom with a considerable amount of residue energy, and the atom will be left in an ionized state. The ejected electron will form its own ionization track, and this track is called the delta ray. If an inner shell electron is ejected, characteristic X-rays or Auger electrons will be emitted, as in the target of an X-ray tube. Energy loss via both hard and soft collisions is referred to as collisional energy loss. Now, when the electron interacts with the atomic nucleus, it's usually deflected with little energy loss. The deflection is expected to be larger for higher Z materials because of the higher charge in the nucleus. And that's the main reason why you have electrons following tortured paths. The scattering mechanism is put to use in the scattering foil. The scattering mechanism is, or in a few percent of the scattering events, Bremsstrahlung emission will occur. And the electrons will lose a fraction of its kinetic energy in the process. And this is an example of inelastic scattering in which some of the kinetic energy is lost. Remember, with elastic scattering, the energy is conserved. Inelastic means that you're going to lose some. This possibility is much more high for high Z materials. Energy loss with this mechanism is referred to as radiative loss. Bremsstrahlung emission does not occur for heavy charged particles because the accelerations in Coulomb interactions with nuclei are much smaller. Now, this leads to stopping power. So the rate of energy lost by charged particles is described as a quantity called the stopping power. It is the kinetic energy loss, or delta T, per unit path length. In other words, how much energy do you lose for a certain amount of distance? There are a lot of subscripts that go along with this, but a lot of those are going to end up getting dropped. This is the primary thing we're going to be interested in. As the particle slows down, the stopping power starts to vary. The units are basically going to be MeV divided by Cm, which are not considered to be SI units, but hey, that's what we're going to use. A lot of times you'll talk about the mass stopping power. Now remember, when it came to the linear attenuation coefficient, and when you divide it by the density, you ended up with the mass attenuation coefficient. Same type of principle here is going to apply. We're interested in being able to get removing the density dependence that might exist here. And so when we take the stopping power and we divide it by the density, we end up with the mass stopping power. And again, when you basically divide by MeV divided by Cm, and you divide that by density, which is going to be grams per cubic centimeter, these are the tortured units that you end up with. So the mechanisms by which electrons lose energy are going to be divided into collisional and radiative. So you got two different possibilities there. So the mass stopping power can be written as the sum of the stopping power of the collision and the stopping power of the radiative. Added those together, you get the total stopping power. Collisional stopping power is roughly proportional here to n sub e times z squared divided by v squared. Z is going to be the charge of the bombarding particle. Now, in many cases, you don't need to confuse the atomic number of the medium and the charge of the bombarding particle. It's trying to write the Z a little bit different there so you don't get confused. You're not looking at the medium it's going into, you're looking at the actual charge of the particle that is doing the colliding. And the collisional stopping power is independent of the mass of the bombarding particle, because you don't see mass written in here anywhere. And that stopping power goes up rapidly as the charge on the ion increases, which would make sense because if you've got z squared here, that charge, whatever that charge is, if it's squared, it's going to be increased because of that exponent. So an alpha particle having the same speed as a proton, and that's important because if you have the same speed here, then that is not varying from each incident. It's going to have a stopping power that's 4 times larger. That alpha particle will have it because its charge is being squared. As a particle slows down, there will be a dramatic increase in the collisional stopping power. And so in 611, which we will get to here, in 611, you're basically seeing the mass collisional and mass radiative stopping power for water and for tungsten. So you have 2 different materials here. You've got water and you've got tungsten. The stopping power, the mass stopping power here for water, if you look at it from the collisional aspect, is going to be up here. As your electron energy starts to increase, your stopping power sort of comes down, but then runs fairly consistently out this way to increasing energies. As far as the radiation stopping power is concerned, you're seeing just a very gradual increase, but the stopping power for collisional is greater until you cross right about here, where the radiative part of water becomes that stopping power, mass stopping power becomes greater. For tungsten, you see basically the same thing where the collisional holds more stopping power than the radiation does. However, the point at which they are equal in terms of MeV is much less than what you're seeing over here. The collisional mass stopping power is proportional to the number of electrons per unit mass of the system. So from equation 6.6, we know here that N sub E is equal to N sub A times Z divided by AW. The atomic weight is equal to the atomic mass number A. And we know that this ratio is relatively independent of Z for Z greater than 1 because A is roughly equal to 2Z. But it's not completely independent. So as the electron nears the end of the ionization track, the stopping power rises sharply. That's because if this is going to be our proportionality, as this gets smaller and smaller and smaller, the stopping power for the collision starts to increase quite a bit. The qualitative explanation here is that the slow electron has more time to interact with atomic electrons in its vicinity. It's not busy driving past it. At low energies, the mass stopping, collisional mass stopping power is inversely proportional to the electron energy. Above the rest mass energy, it's roughly constant with increasing energy. For radiative stopping power, you're looking at that being proportional to Z squared, and therefore radiative losses will be efficient for a high Z medium. High Z targets, of course, you find in X-ray tubes. It also suggests that the radiative mass stopping power is not very important in tissue, which has a relatively low value of Z. It's actually independent of energy for small kinetic energy. For large values of the kinetic energy, then it's proportional. The radiative mass stopping power gives a radiative energy loss rate for a particular energy. The radiative yield is the total fraction of the initial kinetic energy emitted as electromagnetic radiation as an electron slows down and comes to rest. Total energy radiated by each electron is this product. I'm not so worried about you being able to work through too much of the theory here, but you do need to be presented with it in order to be able to kind of see what's going on. Both delta rays and radiative interactions carry energy away from the main ionization track. They don't deposit that energy locally, and so to evaluate local energy deposition, interactions that produce delta rays with energy above some cutoff value should be excluded from the collisional stopping power. So the restricted mass collision stopping power is usually written as this. The restricted mass stopping power is the mass collision stopping power from all soft collisions plus the hard collisions where the energy for the kinetic energy of the delta rays is less than some value. And the typical cutoff here is that value is less than or equal to 100 eV. Now, the restricted mass stopping power is important in beam calibration protocols, and it's used in the definition here of the linear energy transfer. And you can go through some of the description here regarding linear energy transfer. Biological damage is related to the local energy deposition. In other words, the more energy you deposit in a certain amount of mass, the more biological damage you can create. So the linear energy transfer tries to quantify this, and it's defined as this particular product. The density simply cancels in this definition, therefore the LET, the density being here in the numerator, there in the denominator, so you just cancel those out. So the LET is simply the restrictive stopping power in units of keV divided by the micrometers. So it's convenient. It's a convenient measure of local energy deposition. Factor of 10 in the denominator is necessary for unit conversion. The LET does not include energy losses due to delta rays above the cutoff. The LET describes the density of the ionization tracks produced by the radiation. This table lists the values of LET for various types of energies and radiation. The LET for 1 MeV electrons is 0.10 keV per micrometer. When the electrons slow down and the energy drops to 1 keV, oh, these are for electrons, I'm sorry. I was pointing down here, I should have been up here. Then the linear energy transfer rises to 11 keV per micrometer. So the electrons set in motion by cobalt-60 and 200 kVp X-rays have a range of initial kinetic energies, and therefore there's no single value of LET. In other words, it's based on particular conditions. The average LET for cobalt-60 ranges from 0.2 to 7 keV per micrometer. Note how large the LET is for a 2.5 MeV alpha particle. If you look back at the table, you can see it. There's a couple of problems that you can kind of work through here. Those are some pretty significant concepts there. Here's one that's probably a little bit easier to grasp, and it is the range. So if the stopping power of a charged particle did not depend on the speed of the kinetic energy, then we could easily calculate the distance it would travel by dividing its initial kinetic energy by the rate of loss. In other words, the stopping power. The distance that a charged particle travels before coming to rest is called its range. So for example, if the initial kinetic energy of a particle is 5 MeV and its stopping power is a constant 2 MeV per centimeter, independent of it changing its kinetic energy, then the distance it would travel before coming to rest would basically be the 5 MeV divided by the 2 MeV per cm, or 2.5 cm. So the approximate expression for the range is going to be your initial kinetic energy divided by the stopping power. And it can't be quite correct because this depends on this. So as this changes, this will change. It's somewhat different than from the formula that is just given there. The equation 6.16 also assumes what is known as the continuous slowing down approximation, which presumes that energy loss is a continuous process rather than a discrete one due to abrupt collisions. So the assumption of continuous energy loss is probably reasonable when the energy lost in a given condition, in other words, the change is much, much less than what you started out with. This condition no longer holds at the end of a charged particle's path. In other words, when you get towards the end, when you've lost a lot of the energy, then things start to change. And there are some problems here that you can work through. So you can see this figure 6.11 shows the mass collision stopping power, which is dominant, with the dominant contribution to the mass stopping power for electrons in water is approximately constant with energies with energy for energies of interest in radiation therapy. All of that to say this, the rule of thumb here is that the range is going to be basically the energy in MeV divided by 2. So what is the mean energy to produce an ion pair? So the average energy lost by a charged particle in producing an ion pair is given by this formula. This again is the initial kinetic energy of the particle, and N bar is going to be the average number of ion pairs produced by a given type of particle stopping in a specified medium. The average energy necessary to produce an ion pair is almost totally independent of the initial electron energy. So for electrons of charge E, in other words, electron charge, stopping in dry air, then what you're finding here is the average energy lost by a charged particle or an electron is going to be 33.97 eV per ion pair, or 33.97 joules per coulomb. And it's close to the same as electrons in water, and therefore also for tissue, as tissue is mostly water. The value of W bar is higher than the typical ionization potential because some of the energy lost by a charged particle is lost to atomic excitations, thus does not contribute to ionization. So if you look at the example here, how many ion pairs does a 1 MeV electron produce in air along its track and the track of its delta rays? You know what the initial energy is here. You know here what the average energy lost by a charged particle is. So if you take that divided by that, you get this number of ion pairs produced. Now, for those of you that might end up going into proton therapy, this will be of interest for you. Heavy charged particles, including protons, alpha particles, heavy ions, etc. Basically, charged particles except for an electron and a positron. They interact with atomic electrons and nuclei predominantly via the Coulomb interaction, just as electrons do. These particles behave differently in that electrons almost solely, due to the fact that their masses are orders of magnitude greater, about 2,000. Energy loss for heavy charged particles differs because the heavy charged particles tend to have straight ionization tracks. They're not easily bent because they're more massive. The ionization tracks of heavily charged particles are dense, and these often have an ILET. So for two heavy charged particles having the same speed, the collisional stopping power, mass stopping power, is proportional to the charge squared. Multiple charged particles have a particularly high LET. The LET of 5 MeV protons is 8 keV per meter, and for 20 MeV particles, which have the same speed, the LET is 32 keV per meter. At low energies, you can see here is proportional to 1 over the velocity squared. So this implies the energy deposition rate rises rapidly as the particle slows down. Most of the energy will therefore be deposited at the end of the track, which is what's going on here. You have this particle going in several millimeters into whatever it is. You are getting a huge peak of the deposition of the dose, and then it just drops off. This huge peak here, since the velocity gets so low, is called the Bragg peak. Generally, what you want to be able to do is you can't treat with an energy that is almost monoenergetic, because it's your tumor is going to be big and it's going to be spread out over a large distance. So you have to spread that Bragg peak out. And the way you do that is you start varying the energy of those particles that are coming out of the accelerator. And it's useful for certain types of localized therapy. It's preferentially deposited at large depths where a tumor might be located, and at the same time the absorbed energy is relatively small at smaller depths where the normal tissue may reside. So it's a little bit different from photons or electrons. The dose beyond the Bragg peak is essentially zero. Electrons do not exhibit a Bragg peak because they are scattered very easily, and they do not follow straight tracks like heavy charged particles. And you can see here that it mentions spreading out the energies a little bit. The cost of this is to raise the relative dose at smaller depths, and is discussed a little bit further. So this figure here shows the number of particles as a function of depth for photons, electrons, and heavily charged particles. Photons do not have a specific range, and their number declines exponentially. In other words, they're going to decline like this, but they never really hit zero. Electrons have a certain depth at which they cease. Heavy particles travel quite a bit, hit a certain depth, and then peter out. And that's pretty much at the end of their range. And let me back to this sentence. Heavy charged particles decline slowly with depth due to absorption by nuclear reactions at a rate of about 1% per cm for protons in water. Near the end of the range, heavy charged particles, it declines precipitously with depth. So there's a lot going on there in section 6.2. It is, again, trying to describe how charged particles interact with matter. So we'll cover section 6.3 and 6.4 in another video.